Good morning, ladies and gentlemen, and welcome to today's webinar with the topic Flexrigid in combination with USB 3. Over all the different generations of USB specification. So USB 1 was still very slow for few data to transfer, but meanwhile using USB 3 standard or even the latest standard USB 3.1 generation 2, enabling to have a data rate of 10 megabit per second. So this is quite fast, and it's well used standard in the industry. There's also a USB 3 Vision standard serving special issues for cameras. So regarding the power of USB, here we can see a benchmark. Benchmark means transmission of a complete movie with 25 gigabit and using USB 1.1, this took nearly 10 hours. USB 2 reduced the time to more or less 14 minutes, and with USB 3 only 70 seconds are needed to transform these 25 gigabit data. And with the new generation 2 of USB 3.1, also 10 gigabit per second are possible. Of course, 10 gigabit per second is high speed, and this requires specific things for the electronic design. So in the hardware we see that we have two additional wires, and these are performed as differential pairs. So for the high-speed transmission via USB 3, we have 4 high-speed wires. The specification for USB universal serial bus in electrical manner is that we need a differential impedance controlled structure with 90 ohms. Often there are also signals using the LVDS specification. For this we also need a differential structure, but with 100 ohms. So the two slides on the bottom I've taken out of the USB implementation forum's presentation from last year in Hong Kong, and we can see on the left side in the red area the requirements for the system. You have to take care of losses on the PCB, for example, or on cables, in connectors, as well as reflections and crosstalk. And on the right side we can see for the PCB it's important to care for the stack up. For any issue we have to take care for trace length and take care for the dielectric materials and wires. So that's for the printed circuit board, but at the same time we have to care for the connectors, especially if they are used inside the system. So we will come to that point afterwards. One approach to meet these requirements is to use Flexrigid technology. Flexrigid technology helps to avoid connectors and discontinuities along cables and connectors. So this improves signal integrity in a second. And the other thing is to use microwires. So short stubs have less disturbing the signals. So avoiding of through-hole vias whenever it is possible, helps to improve signal integrity. Using Flexrigid technology in the same moment means usage of low-loss material, which is called polyimide. So this thin foil, flexible material shows pretty good performance regarding high frequency. So we will see some figures afterwards. And again, the point using Flexrigid technology means that we can avoid the weak points, connectors. So on this slide of the USB implementation forum, there is a proposal replacing long PCBs by an internal cable. But doing this, that means we also need, besides the cable, we need two connectors, and we will see how connectors perform in general and especially in USB technology on the next slide. So this is a measurement, TDR measurement along a complete system with a test fixture, a plug, a PCB, receptacle, and a cable in between. And we can see that besides in the area where the connectors are located, we have a big disturbance in the signal. So every plug could not be as good as the PCB in this case. So using Flexrigid technology finally can eliminate the weak point connector. Signal integrity using Flexrigid. The major topics are impedance power matching. So we will see that on the next slide how this could be done. The timing is very important. We can see on the bottom some examples of matching trace length with differentials pairs. So in this case, it's really helpful to have an EDA tool which supports the design of differential pairs. The example in the middle is taken from Altium. And the third point is we have to care for reflections. Tip at that topic, we already have performed in webinar, and a webinar which you can find in the webinar archive about Flexrigid technology and signal integrity. So there you can find even more information about this. So the specialties with Flexrigid, we are using a thin flexible material which is called polyimide, and in general this performs good for high frequencies, as we can see there are small losses due to a small value of the loss tangent. On the right bottom chart we can see it's around about 0.004, the loss tangent, so that's pretty good compared to a standard rigid material. And the other point is we have also small losses due to a very low treatment profile on the copper. So this also helps to have a pretty good signal integrity on the flex material. So in general, we have the need of actions in the design because this flexible material is very thin, and so typically 50 micron thickness, could be 75 or 100 micron, but that is more expensive. On the other side, we have a small value of the dielectric constant, epsilon r, which is round about 3.4. So how can we meet the requirements of high frequencies? We have to ensure that the impedance in the rigid area as well in the flexible area is the same. So we have to ensure that we first define the target impedance value, which is 90 ohms differential structure for USB. Then we have to choose a practical impedance model for the layout. We have to choose the thickness of the polyimide. The standard thickness is 50 micron, but 75 micron helps to get wider traces in the design. So that's better for the production and for the yield. At the same time, we have to ask whether there are mechanical requirements like bending, small bending radii, or even dynamical bendings. So this has to be taken in consideration. Then we can simulate to fit the line width. And finally, there is the option of using a hedged reference layer to increase the impedance so that we do not have to take pretty thick polyimide, which is very expensive. So these are the actions which are needed and which are possible to meet the signal integrity requirements for high speed. Regarding the layer configurations, in most designs, 2 layers in the flexible area are sufficient. So with 2 layers in the flexible area, we have a so-called XRI to FXRI construction, and we can use, for example, a edge coupled coated microstrip with 1 reference layer. Typically, the flexible layer is inside the stack up, symmetrically inside, could also be external, as we can see on the second example, the FR4 semi-flex with the 2 bendable layers outside. If we have more copper layers in the flexible area, we can also use strip line configuration, for example, with 2 reference layers. So the example shows a so-called 1RI 6F 1RI construction, which means 8 layers in the rigid area and 6 layers glued together in the flexible area. How do we calculate the parameters for the design to meet the impedance requirements? We are using a tool like you can see here, and the effect on the design structures we can see on the right side. Based on a 50 micron polyimide film, we can see 3 different line widths, 6 mil, 150 micron, in gray, in black we can see a 5 mil line, and in red we can see a 4 mil or 100 micron line. If we need 90 ohms differential impedance, we can see that we can hardly meet that. So the impact of the value of the separation between the 2 differential lines is not that much. So in this case, we have different possibilities. We can use even thinner lines. That's one possibility. We can use a thicker polyimide, which is more expensive, or we can use a hedged reference layer, which also increases the impedance value. So it's up to a discussion which way has to be followed. Now we'll show you a concept for the flow of within the design chain. So regarding the complete design chain of an electronic system, we have also performed a webinar in the past, and you can find the link in the PDF document you will receive after this webinar. So the red points within the design chain are including relevant input for the following approach for the signal integrity. So specification is important. We also will care for the mechanical design. We will care, of course, for the electronic design, the PCB layout, the production, and the test in that way that we can perform a impedance measurement. The first point is the question which components have to be rooted on in the design, and the most complex component defines the stack up. So the more complex the component, the more complex the used stack up. And in the first approach, we will look within the standard stack ups to find a stack up meeting the requirements of the components. And at the same time, this defines the wire technology, whether we can stay with standard through-hole vias or whether we have to use microwires or even buried vias or stacked microwires. Mechanical design, it's important to meet cost optimization, and to do that, and therefore it's important to check the area consumption of the design, as well the question whether we need additional areas on the production panel for the test coupons if they are needed. I will show some examples afterwards. The next step regarding the specification for the signal integrity means that we have to adapt the standard stack up to meet the signal integrity requirements. Then we will perform an impedance calculation and providing finally a documentation with all the information inside to you. And after that, it's possible to make a quote for this Flexrigid PCB. So then you can order this PCB with the complete impedance documentation. We can produce a PCB, and the question is whether that's produced with or without test coupons, and whether we have to perform an impedance testing measurement or not. Maybe only for prototypes, but not for serial volumes. So that's part of a discussion, and it's of course important for the cost optimization. Here we can see a standard stack-up plan for Flexrigid technology. In the rigid area, we have 8 copper layers. In the flexible area, 2 copper layers based on TG 150 material, halogen-free and filled. The copper thickness on inner layer standard is 18 micron. Tip at that point, if you have inquiries regarding complex designs or signal integrity things, please use our team address, which is flex@we-online.com. So this ensures a pretty fast caring for your inquiry, as the complete team has access to this team address. Mechanical design. So the question is, how much area do we need for your special design approach? And assuming that we have 6 rigid parts, there are different possibilities to combine these rigid parts. One of these possibilities is called cross. You can see it here. Now, looking forward to the production, we have to state that this design is not the best we can imagine, as finally with nesting there is still a lot of area which could not be used for production. So a slightly better design is the so-called L form. That's even better to nest, especially for these two PCBs nested. Maybe if we want to use the complete area, we have the chance to have a third PCB on the panel, but that's it. So still some area left we cannot use. Maybe we can use that for test coupons, but it's not usable for PCBs. A better design is the line design. Here you can see immediately that we can have even 4 complete PCBs on the production panel. And an alternative to the line design is the matrix design, so matrix 2 times 3. In this case, very advantageous to bring it on the production panel. So again, 4 PCBs on the available area. So the next step is the adjustment of the stack up to meet the impedance requirements. So we have to care for dielectric thicknesses for wires which are used. We have to look at the rigid area as well as on the flexible area. And after the adjustment of the stack up, we then can do the calculation and documentation. So this looks like you can see here on this slide. This is the rigid area. Here we can see the different materials and thicknesses which are used, as well as the red figures showing us there are 17 different impedance models used. We have to calculate and documentate. So that's done here, and in this documentation you can find the values for the line width and the separation values for your layout design. Same for the flexible area, showing the stack up with all the important values for the calculation, and as well for 6 impedance models which are calculated, their values for line width and separation. So this was a lot of theory and discussion, and now let's have a look at 2 applications. So the first application, we can see here, the picture is not out of this application, but shows pretty good the situation we had in this project in the starting point. There are a lot of independent modules, rigid modules, combined by flat cables and connectors. And on the top you can see the form modules we had in this project. There was a power board with 8 layers. There was a connector board with 10 layers, already using controlled impedance structures on that. We had a controller board with an FPGA, 16 layers, very complex, also controlled impedance, and finally we have had a sensor board with 10 layers and also controlled impedance structures. Of course, the combination, the connecting of the modules is necessary, which is not that critical between the power board and the connector board, but between connector board and controller board, there we already need a high-speed cable and connector, which is very expensive, as well as for the connecting of the FPGA board and the sensor board. So the question at that point was, is it possible to miniaturize the complete system, to make it remarkably smaller, to make it to improve it in terms of performance as well, and of course, the question, how much would this cost if we would change from this existing situation to a Flexrigid design? So the approach was to use 4 layers in the flexible area, and immediately you can see now all rigid areas have the same layer count, 14 layers of course, and 4 layers in the flexible area. So this is called, with 14 layers, is called a 5RI, 4F5RI. And here we can see the stack up as it is used in the calculation tool for the impedance. So now it's one part, no more connectors, no more cables. So this makes the design easier and also the handling and the performance better. Finally, the solution looked like this. We could meet all requirements with only 12 layers. So that means 12 layers in the rigid area and 4 layers in the flexible area. And this is a picture from the PCB showing the delivery panel prior to the assembly. And this is how the impact was on the final product. On the right side you can see the old situation, and on the left side you can see the new situation. So this is a big success in terms of miniaturization as well as improving performance and testability. The second application, now we are back with USB 3. So this is a USB 3 camera using the USB 3 vision standard. And one really important thing is that the micro connector for USB 3 is placed on a separate rigid part. So nearly every orientation and angle in the housing is possible using this Flexrigid technology. And we have an impedance matched connection between the connector, USB connector, and the USB driver, which is very important. We also succeed to avoid internal connectors and cables. So this provides an excellent performance, a good testability, and a good robustness for this system. So, by the way, the system is around about 28 millimeters by 28 millimeters by 28 millimeters. So it's really, really small. So now let's come to the summary. Flexrigid for high data rates, for example, USB 3, means that this requires an improved PCB solution, and improved PCB solution means for me Flexrigid technology, as this Flexrigid technology shows intrinsic advantages which are really improving signal integrity for these high data rates. At the same time, we have to consider that the complexity of electronic design and development requires a really close cooperation with the PCB producer. So it's important to come into a close discussion in a very, very earlier phase of the project, as we have to discuss stack-ups and design parameters. So we as Würth Elektronik have a lot of experience in the production of impedance-controlled Flexrigid printed circuit boards. So please ask us. We would really like to help you in your development. And last but not least, a short look into the future for the implementation of the USB 3.1 Generation 2 standard with 10 gigabit per second data rate. I think that especially for miniaturized systems, Flexrigid technology will be a really enabling technology, making solutions small with a good performance and with a high reliability. So I hope that was interesting for you, and now I give the word to Mr. Walz. Thank you very much for your attention.
And now I would say that we start with the question and answer session. The first question was, is LVDS additional signal needed for USB 3?
Good question. So LVDS is used not for USB, but is used for communication, for example, of optical sensors. And so, of course, due to the different specification, you need additional lines for LVDS, and this needs 100 ohms differential pair constructions. So that's not the same. It's used for different protocols and different applications, but it's possible to combine this in one design.
All right, okay. And so another question is that we have here, you mentioned a hatched GND plane to increase the impedance. Is this technique fully under control? Can it be calculated in polar? What about the EMI if a high impedance GND is used?
A lot of questions. Let's start with the easiest point. Yes, we can calculate hatched ground planes with our tool, as we have the hatch option already integrated in our Polar system. The recommendation is to use slightly hatched reference planes. So round about maximum 70% copper coverage. So it's not recommended to use less copper coverage than 70%. And we already had a lot of projects with different customers, and the hatching worked well. Finally, to be honest, we don't have experience with USB 3.1 generation 2. So with really 10 gigabit per second, we don't have experience with hatched reference planes today, but we would really like to test this with you.
Thank you. So another question is, how many different kinds of flex materials are commonly used? Temperature limitations?
Oh, yeah. As a hint at that point, we also have performed a webinar in the past concerning all the materials which are used for Flexrigid technology. So please have a look into the webinar archive. Regarding the materials, the flex materials, it's always polyimide in this Flexrigid combination, and our standard always is to use adhesiveless polyimide material. There are different suppliers, but they are really comparable regarding signal integrity. So, for example, one standard we are using is DuPont material Pyrolux AP. You can find the data sheet in the internet. Regarding the temperature resistance of polyimide, that's pretty much better compared to a rigid material. So if we are talking about rigid materials with a TG of 150 or maybe 170 degrees C, polyimide has a TG of much more than 300 degrees C. So in the complete system, the flex material never is the weak point. It's always the rigid material. So don't argue. There's no problem with the flex material.
All right, thank you. So another question is there a max length for USB 3 signals on a PCB before having communication problems?
Good question. Yes, definitely there is a maximum length if we regard also the losses. But to be honest, in our impedance calculation, we assume that the lines are without losses. So on the other hand, if we have Flexrigid technology, we always have very small and compact solutions. So until today, we never have had problems with signal integrity issues. So there is a limit definitely regarding cables, for example, for USB 3. The cable maximum is allowed to have 1 meter without repeaters. So 1 meter is a long way for a PCB. So let's say in that way we never had problems with Flexrigid PCBs.
Okay, so then another question is it possible to have a good performance for USB 3 with FR4, or do you have to use material like PTFE?
Oh yeah, so that's the same direction of the question regarding the losses in the material. As I tried to show you, the polyimide itself is a low loss material. So the question is about the combination with which rigid material we can get a good performance. So USB 3 still works pretty fine with standard FR4. I don't know an application using USB 3 which is based on PTFE material or other mid or high performance materials. So that's only needed for really big PCBs.
All right, and so we have one last question. What is about the behavior to vibration standards such as MIL 810G?
Okay, so to be honest, I don't know the standard in my mind, what it exactly specifies, but vibration in general, if you have external impact on the system, Flexrigid has a big advantage as the flexible areas which are doing the connection between the rigid parts have a very low physical mass. So the risk that they start to move is very low. By the way, we already did another webinar about the reliability issues. You can find this webinar also in our webinar archive, and I will send you an email with the link to find this very shortly. So finally, Flexrigid is pretty good for vibration, so very reliable.
Okay, now we have received another question. Is it better to reach flex layer with USB 3 signals as soon as possible to have better performance?
Generally, yes. So short lines are always better as long lines. Of course, losses are smaller, and all other effects like reflections could be reduced. So, but I think it's more important to have a look at the wire technology. So avoid long stubs, standard through-hole vias wherever possible. But of course, finally, you are right. It's always preferable to have short lines. So that's the reason that the USB driver normally is very close to the outline of the rigid part, and you can see it also at our second application I've shown you in the webinar.
All right, thank you, Mr. Schilp. So now we have answered all the open questions at the moment. If anything else will come up on your mind, please do not hesitate and contact us by mail. You have the addresses right on the screen right now. So I want to thank you all for your participation. Mr. Schilp, I want to thank you for your presentation and the answering of all of the questions. So it would be a great pleasure to see you in one of our next webinars again. Until then, have a good time. Goodbye.